Welcome back to the deep dive. Today we are stripping away the metaphor,
Which one?
the big one. You know, when we talk about the heart and circulation, everyone defaults to this very simple, almost industrial image.
The pump in the basement.
A pump in the basement and some copper pipes in the walls. It's plumbing, pure and simple.
Right. Simple hydraulic engineering. Input, output, flow. Done.
But looking at the stack of research we're covering today, and we are going heavy into the medical canon here, specifically Ganong's review of medical physiology and the legendary Guyton et al. Textbook of medical physiology, that plumbing model isn't just a little bit off.
It's not just off. It's actually misleading. It's way too static.
It misses the entire point.
It misses the sophistication entirely. I mean, if you treat the cardiovascular system like copper pipes and a water pump, you can't explain why you don't pass out every time you stand up.
Right.
You can't explain why your ankles swell on a long-haul flight.
Yeah.
You certainly can't explain how you're alive right now, given the sheer forces involved.
So here is our mission for this deep dive. We are going to look at circulation not as a static loop, but as a dynamic, sometimes violent, and surprisingly delicate partnership.
I like that.
And we've broken this down into 3 pillars based on the texts: force, form, and fluid.
That's a great framework. It really helps organize the chaos. So force is the engine, the heart itself,
The pump.
the pump. And for that, we're really leaning on Ganong's chapter, The Heart as a Pump. It gives you this incredible mechanical precision.
And then form.
That's the vessels, the pipes, which, as Guyton shows us in the chapters on vascular distensibility and the microcirculation, well, they're not pipes at all. They're living, reacting organs that change their shape constantly.
And fluid, which is a huge piece of this. It's not just the blood flowing through, but the fluid leaking out, the fluid being reclaimed, and all the physics that keeps us from, just swelling up.
Exactly. We're going to synthesize the mechanistic detail of Ganong with the systems-level regulation of Guyton.
Yeah.
But I think we need to be clear right up front.
Go ahead.
What we are doing today is an interpretation and a synthesis. We're building a conceptual map for you, the listener. We are not replacing the text.
Absolutely not. You cannot learn physiology just by listening to 2 people talk. You have to look at the graphs.
Yeah.
You have to actually see the pressure volume loops that we're going to describe.
Consider this episode a scaffold. We're going to build the structure in your mind so that when you go back and read Ganong and Guyton, and you really should, the details will have a place to live. They'll make more sense.
Okay, so let's start with what I think is the central tension of this entire system. Reading through these chapters, I was just struck by this massive contradiction.
Which is?
The heart is violent, it generates this huge explosive pressure with every beat, but the destination, the capillaries in your brain or your kidneys, is incredibly fragile.
That is the core engineering challenge of the whole system. You have to take a high-pressure pulsatile explosion, which happens about, 70 times a minute?
Yeah, once a second, basically.
And you have to smooth it out into a gentle, continuous stream by the time it reaches the cells. If that raw force hit your capillaries directly, they just burst. They'd shred.
So the system is, first and foremost, a dampener.
It's a dampener, it's a distributor, and it's a scavenger. It has to leak just enough fluid to feed the cells, but then reclaim enough so you don't turn into a water balloon. It is walking a tightrope every second of your life.
Let's get into the mechanics. Section 1, the engine. We're drawing heavily from Ganong here for the nitty-gritty. And the first thing that jumped out at me was the timing.
Right.
We tend to think electrical spark happens, muscle squeezes, boom, boom. It feels instantaneous.
It is simultaneous in our perception, but physiologically, there is a very precise sequence. Ganong makes a huge deal about this electrical mechanical link.
Okay.
The electrical depolarization, that's the spark, is what triggers the mechanical contraction. But here is the key difference between your heart and, say, your bicep. In the heart, that contraction lasts a really long time.
How long are we talking?
Well, it starts just after depolarization, as you'd expect, but it continues until about 50 milliseconds after the electricity has already reset, after repolarization is complete.
Wait, hold on. So the electricity has already given the all-clear signal, the wave has passed, but the muscle is still squeezing.
For 50 milliseconds, yes. And this is absolutely crucial because the heart can't just twitch. A simple twitch doesn't move blood against the massive resistance of your arteries.
It wouldn't be powerful enough?
Not at all. It has to wring itself out like a dish rag. It needs that duration to actually build pressure and empty the chamber.
So let's walk through a single beat, not the lub-dub sound, but the physics of it. Ganong breaks the cardiac cycle into these distinct phases of pressure and flow. I want to zero in on the start of the squeeze. Systole.
Okay, so picture the left ventricle. It's just filled up with blood. It's relaxed and full. Then the electrical signal hits.
The spark.
The spark. The muscle fibers start to shorten. And the pressure inside that chamber starts to rise immediately. The very first thing that happens is this rising pressure slams the mitral valve shut.
So the door back to the atrium, the filling chamber, is closed and locked.
Right. But, and this is the most dramatic part of the whole cycle, the door to the exit, the aortic valve, hasn't opened yet.
Why not?
Because the pressure in the ventricle, even though it's rising fast, is still lower than the pressure in the aorta that's sitting on the other side of that valve. There's back pressure from the whole system.
So you have a sealed chamber.
A completely sealed chamber. The walls are squeezing in, but the blood has nowhere to go.
This is what Guénon calls isovolumetric ventricular contraction.
Let's break that down. Iso meaning same, metric meaning length, or in this case, volume. The volume of blood doesn't change. Not a single drop leaves.
But the pressure.
The pressure skyrockets. It goes from maybe 5 millimeters of mercury up to 80 in a fraction of a second. It is essentially loading a spring. The heart is building up kinetic energy, straining against these two closed doors.
And it has to hit a specific number, a threshold, to blow that exit door open.
It has to exceed the diastolic pressure in the aorta. For most people, that's around 80 millimeters of mercury. The very instant the ventricular pressure hits 81, the aortic valve pops open.
And that's the release. That's ventricular ejection.
And chaos ensues. Blood just rushes out.
Huh.
But here is a beautiful detail in Guénon that most people miss, and it's pure physics. We usually assume blood flows from high pressure to low pressure.
That's the basic rule of plumbing, right? High to low.
Generally, yes. It's the path of least resistance.
Yeah.
But late in systole, toward the very end of the squeeze, the pressure in the aorta is actually higher than the pressure in the ventricle.
That doesn't make any sense.
It shouldn't.
If the pressure is higher outside, the blood should fall back into the heart. The valve should slam shut.
It should. But it doesn't because of one word: momentum. The heart pushes that column of blood so hard in the beginning that it accelerates it. That moving column of blood has mass and velocity. It's like a freight train. It's like a car coasting uphill. Even though the gradient, gravity, is against it, the momentum carries it forward for just a brief moment longer.
That is fascinating. The heart hits the blood so hard that it briefly defies the normal pressure gradient.
Exactly. But of course, momentum eventually runs out. The blood slows, stops, and tries to flow backward. That backward flow is what catches the little pockets of the aortic valve, and snap, the valve closes. That sharp closure is what creates the dicrotic notch you see on an arterial pressure tracing.
And now we enter diastole. Relaxation. I always thought this was just the heart, resting, taking a break. But reading the text, it seems like diastole is a pretty active process.
It absolutely is. So the ventricle starts to relax, but again, for a moment, both valves are closed.
Yeah.
This is isovolumetric relaxation. Pressure drops like a stone from 120 down to near zero, but the volume stays constant.
So it's the mirror image of the contraction phase.
Perfectly. Then, once the pressure inside the ventricle falls below the pressure in the atrium, the intake valves, the AV valves, drift open, and we get the rapid filling phase.
And Guénon mentions a suction effect here. It's not just passive filling.
That's right. The heart muscle doesn't just relax, it actively uncoils. It's elastic. It springs back into its resting shape, and in doing so, it actually pulls blood into the ventricle. It creates a small vacuum.
So now I have to ask you about the atrial kick.
Ah, yes, the famous kick.
The sources seem to really downplay it. We're taught in biology class that the atrium contracts to push blood into the ventricle. It's this important final step. But Guénon says it's only responsible for maybe 30% of the filling.
Even less in some conditions, maybe 20%. About 70 to 80% of the filling is totally passive. It's just gravity, and that suction effect we talked about. The atria contracting only serves to top off the tank.
It's just a little extra push at the end.
It's a final squeeze. This is why people can live for years with atrial fibrillation, where the atria just quiver instead of pumping properly. You lose that kick, so you might get winded running up a flight of stairs, but for sitting here recording a deep dive, you're perfectly fine. The system is over-engineered. It has redundancy.
I want to try and visualize the pressure volume loop for the listener. This is the diagram that every medical student has nightmares about, but it's actually a beautiful map of everything we just discussed.
It's the single best way to visualize the work of the heart. So imagine a graph. On the x-axis, the horizontal one, you have volume. How full is the heart?
Okay, more volume to the right.
Exactly. And on the y-axis, the vertical one, you have pressure. How hard is it squeezing?
Higher pressure is higher up the graph.
Got it. So let's walk the loop. We start at the bottom right corner. The heart is full of blood, but the pressure is low. This is the end of diastole.
Ready to go.
Ready to go. Now, the first thing that happens is we move straight up. The line goes vertically. Pressure rises, but volume stays the same.
That's our isovolumetric squeeze we talked about, the sealed chamber.
That's it. Then we get to the top of the graph, and the line turns and moves to the left.
So now pressure is staying high, but we're losing volume.
Volume is dropping as blood is ejected into the aorta. That's ejection. Then, from the top left corner, the line goes straight down.
Pressure drops like a rock, but volume is constant because the valves are closed again.
It's a volumetric relaxation. And finally, the line moves across the bottom, back to the right, as the heart fills up with blood again at low pressure. It makes a sort of tilted box.
And the really key insight here, the reason this graph is so important, is the area inside that box.
Yes, the area inside that loop represents the physical work the heart does in one single beat. If you have high blood pressure, for instance, the box gets taller. The heart has to generate much more force to open that aortic valve.
And if you exercise,
the box gets wider. You pump more volume with each beat. The loop expands to the right.
This leads us directly to the clinical reality of heart failure. And Ganong distinguishes between systolic and diastolic failure. Using the loop, this distinction finally clicked for me.
It's a perfect illustration. Systolic failure is a pump problem, a squeezing problem. The top of the loop collapses, the muscle is weak and can't generate enough pressure, so the ejection fraction, that's the percentage of blood pumped out, drops way below the normal 65%.
The box gets shorter.
Exactly. Now, diastolic failure is different.
That's a filling problem.
It's a filling problem. The heart is stiff, it's non-compliant, it squeezes just fine, maybe even too hard, but it can't relax properly to accept the blood.
So the loop gets narrow.
The loop gets narrow because you didn't start with enough volume in the first place. The starting point on the x-axis shifts to the left. Stroke volume is low, not because the pump is weak, but because it wasn't loaded properly. It's the difference between trying to squeeze a full water balloon versus trying to squeeze a nearly empty leather boot.
There was one term in Ganong regarding acute failure that sounded like something out of science fiction. Myocardial hibernation.
Isn't that wild? It's a fantastic concept. In conditions of severe stress, like sepsis or a major heart attack where there's a lack of blood flow, the heart cells realize they are starving.
They're not getting enough oxygen.
Exactly. So they intentionally downregulate their own function. They stop contracting as hard. They essentially play dead to conserve what little energy they have and avoid cell death.
So on an echocardiogram, it would look like severe heart failure, but it's actually a strategic retreat.
It's a survival mechanism. Biology is so much smarter than we are. It shuts down the factory to save the machinery, hoping that blood flow will be restored.
Okay, listener, take a second and let that sink in.
Yeah.
We've just built the engine. We have a pump that uses electricity to trigger a timed, powerful mechanical squeeze, manipulating pressure to move volume. Now, that blood leaves the heart and enters the pipes.
And this brings us to section 2 and squarely into Guyton and Hol.
And here we have to untangle two words that people, and I'm guilty of this, even doctors, use interchangeably, but Guyton insists are totally different: distensibility and compliance.
This is such a critical distinction. It feels like semantics at first, but it changes how you understand the entire system.
Okay, so let's define them one by one. Distensibility.
Distensibility is just stretchiness. It's a property of the material itself. The question is, if I increase pressure by 1 millimeter of mercury, by what fraction does the vessel expand? Guyton states that veins are about 8 times more distensible than arteries.
They're just floppier, softer material.
Much floppier. Arteries are thick and muscular, veins are thin and baggy.
Okay, so veins stretch easier. Then what on earth is compliance?
Compliance is the total amount of blood the vessel can hold for a given pressure change. It's the total storage capacity. The equation is simple. Compliance equals distensibility times volume.
So it accounts not just for the stretchiness, but also for the size of the container.
Precisely. And because veins are not only more distensible, but also much larger in volume than arteries, their compliance is massive.
Guyton gives a number that's pretty staggering: 24 times.
The compliance of the systemic venous system is 24 times that of the arterial system. This is why we call veins the capacitance vessels. They're the storage tanks of the circulation. Over 60% of your blood is in your veins at any given moment.
And this is what explains why you can donate a pint of blood and, feel a little lightheaded, but be basically fine.
Exactly. Guyton notes that the system can function almost normally, even if you lose 20 to 25% of your total blood volume,
How is that possible?
because the veins are holding all this extra reserve blood. When you hemorrhage, your sympathetic nervous system kicks in and clamps down on the veins. It squeezes that reservoir, pushing the stored blood into the arteries to keep your blood pressure up and keep your brain alive.
It's an emergency backup tank built right into the system.
A huge one.
But let's flip to the other side. The arteries. They aren't storage tanks. Guyton calls them pressure dampers.
Right. Remember that violent pulsatile explosion from the heart? If that pressure wave hit the capillaries, it would act like a jackhammer. The job of the major arteries, especially the aorta, is to turn that pulsatile flow into continuous flow.
The famous Windkessel effect, the
Yeah.
air chamber effect.
Yes. When the heart squeezes during systole, the elastic wall of the aorta expands like a balloon. It accepts that stroke volume and stores some of that kinetic energy in its stretched walls.
It absorbs the shock.
It absorbs the shock. Then when the heart stops and relaxes during diastole, the aortic wall recoils, squeezing that stored blood forward. It acts like a second pump, smoothing out the wave.
And Guyton paints a pretty grim picture of what happens when this function fails in arteriosclerosis.
Stick pipes. It's the perfect example. With aortic disease, the aorta loses its elasticity. It loses compliance. It becomes a rigid steel pipe.
So what happens to the pressure?
Well, during systole, because the wall won't give, the pressure has to shoot up dangerously high to accommodate the blood. Your systolic pressure might go to 180 or 200.
Then during diastole.
During diastole, there's no elastic recoil to push the blood forward, so the pressure plummets. Might drop down to 60 or 50.
So the pulse pressure, the gap between the top and bottom number, gets huge.
It becomes massive. And that surging, hammering flow is incredibly damaging to the delicate vessels in the kidneys and the brain over time. Form failure leads directly to organ failure.
Before we move on from the pipes, there's a fascinating concept in Guyton regarding veins that I found super counterintuitive. It's called delayed compliance or stress relaxation.
This blew my mind the first time I read it. It implies that the vessels are actively changing their size over minutes and hours, not just passively stretching.
So how does that work? If a doctor gives you a big bag of IV fluids quickly,
Right, if I inject a huge amount of fluid into your veins, your pressure spikes, as you'd expect. But if you just wait 10 or 20 minutes, something amazing happens. The smooth muscle fibers in the vein walls slowly creep or lengthen. They relax to accommodate the new, larger volume.
the container actually creates more space for the fluid.
Automatically. And your pressure drops back down toward normal, even though you have more volume. It also works in reverse. If you lose blood, the vessels slowly creep tighter over minutes to hours to help maintain pressure. It's a dynamic, self-adjusting system. The pipes are alive.
That's incredible. Okay, so moving to section 3. We've talked about the pump and the pipes. Now we have to talk about the single biggest enemy of circulation.
Gravity.
Gravity, the silent killer.
It really is.
Guyton breaks down the physics of hydrostatic pressure, and it's simple, really. Blood is heavy, it's a fluid, it has weight.
It's a fluid column. In a standing adult, the weight of the column of blood from your heart down to your feet creates about 90 millimeters of mercury of pressure in the veins of your feet.
90. That's almost equal to the mean pressure the heart generates to push blood forward.
It is. It's a massive opposing force. So if you stand absolutely still, and the classic example is a soldier standing at attention, that 90 millimolar G is constantly pushing fluid out of your capillaries and into the tissues of your leg.
You're just leaking fluid.
You are. Guyton estimates you would lose 10 to 20% of your effective blood volume into your leg tissues within just 15 to 30 minutes.
You'd swell up and then you'd pass out from low blood pressure.
Which is exactly what happens if you lock your knees and stand perfectly still for too long. To prevent that, you have to keep the venous pump working.
Which we also call the muscle pump.
The muscle pump. Every time you twitch a leg muscle, even slightly, you squeeze the deep veins in your legs. Now, because veins have one-way valves every few centimeters, that blood can only go one way.
Up, towards the heart.
Up. It's like climbing a ladder. You squeeze, the blood goes up a rung.
Yeah.
You relax, the valve catches it and holds it there. You squeeze again, it goes up another rung.
Guyton says that just the simple act of walking keeps the venous pressure in your feet below 20 mmHg.
It's incredibly efficient. It basically negates the entire effect of gravity, unless, of course, the valves fail.
And that's varicose veins.
That's the pathology. The valves become incompetent. They stretch apart. Now, when you squeeze, the blood goes up. But when you relax, it falls right back down. The pressure stays high all the time, the veins get distorted and tortuous, and you get chronic swelling or edema. The hydraulic ladder is broken.
One last detail here that I found surprisingly philosophical was Guyton's discussion of the zero reference point. Where is zero pressure in the body?
It's a great question. You need a stable reference point to measure everything else against. And for the circulatory system, that point is the tricuspid valve, the entrance to the right ventricle.
Why there specifically?
It's the physiological anchor, because the heart itself acts as a feedback regulator right at that spot. If pressure at the tricuspid valve rises for any reason, the right heart stretches more and pumps harder to lower it. If pressure falls, blood dams up in the veins until it rises back to that set point.
So the body defends the pressure at that one point above all others.
It does. No matter if you are lying down, standing up, or hanging upside down from a tree, the body fights to keep the pressure at that specific valve stable. It's the true north of the circulatory system.
Right, we've covered the engine and the pipes. Now we finally arrive at the destination. Section 4, the microcirculation.
The business end. Everything else, the heart, the arteries, the veins, it's all just logistics to serve this one area. This is where the trade happens.
And the scale here is just hard to get your head around. Guyton says we have something like 10 billion capillaries.
With a total surface area of about 500 to 700 square meters. That is roughly 1/8 of a football field tucked inside your body. And here is the fundamental rule of this design. Almost no cell in your body is more than 20 to 30 micrometers away from a capillary.
It's an incredibly intimate delivery system. But what surprised me is that blood flow in these individual capillaries isn't a steady stream. Guyton calls it vasomotion.
It blinks. It's intermittent. At the entrance of a true capillary, there's a structure called a precapillary sphincter. It's just a tiny single ring of smooth muscle, and it opens and closes several times a minute.
What controls the blinking? Is it the nervous system?
Not directly. It's mostly local. The primary controller is oxygen concentration in the tissue itself.
So it's a feedback loop.
A beautiful, simple feedback loop. If a tissue is metabolically active and uses up its oxygen, the local oxygen level drops. That drop in oxygen causes the sphincter to relax. The gate opens, fresh blood rushes in, and oxygen is delivered.
And once oxygen levels are restored,
the sphincter cramps shut again. So your blood flow is literally following your metabolism, second by second, micrometer by micrometer.
That's just-in-time delivery at a microscopic level. The body doesn't waste energy pumping blood to cells that don't need it right this second.
It's the ultimate inefficiency.
Now, the capillary walls themselves, they aren't all the same, are they? Guyton points out that the porosity, the leakiness, changes dramatically depending on the organ.
Form follows function again. This is one of those recurring physiological themes we see everywhere. Just look at the brain. The endothelial cells that form the capillary wall are fused together by tight junctions.
A fortress.
An absolute fortress. Nothing gets through the gaps between the cells except water, oxygen, CO2, very small lipid-soluble things. Everything else has to be actively transported. That's the blood-brain barrier.
Now compare that to, say, the liver.
The complete opposite.
Yeah.
In the liver, the clefts between the cells are wide open. They are massive gaps.
Yeah.
Even huge plasma proteins like albumin can float in and out of the bloodstream freely.
Why would it be so leaky?
Because the liver's job is to process those proteins and other molecules in the blood. It needs full, direct access. If the liver capillaries were a fortress, the hepatocytes couldn't do their job.
And the kidney.
The kidney is different again. It has fenestrae. These are little windows or pores that go right through the body of the endothelial cells. They're designed for rapid filtration of huge volumes of fluid.
It's amazing engineering, using the same basic building blocks, endothelial cells, but just tweaking the mortar between them to completely change the function.
Precisely. It's elegant design.
Now we have to get into what is probably the most complex part of the fluid dynamics, Section 5, the Starling forces.
The tug of war. This is a set of 4 pressures that determines moment to moment whether fluid stays in the blood or leaks out into the tissue.
Let's break them down simply. Force number 1, capillary hydrostatic pressure.
That's just the blood pressure inside the tiny tube. It's the force pushing water, OUT, of the capillary, filtration.
Okay. Force number 2, interstitial fluid hydrostatic pressure, the pressure of the fluid outside the tube.
Now, this is the weird one. You'd think it would be positive, pushing back. But in most loose tissues, this pressure is actually negative. It's a slight vacuum. So it also acts to suction fluid, OUT, of the capillary.
Wait, so both of those forces are pushing fluid out? If that's all there was, we'd dry out in minutes.
We would. So there has to be a force pulling it back. That's force number 3, plasma colloid osmotic pressure.
The sponge effect.
The heavy lifter. The sponge effect is the perfect way to put it. Albumin and other big proteins are too large to easily leave the capillary. They are stuck inside the blood. By the laws of osmosis, they pull water towards them. They suck fluid back in.
And the final one, force number 4, interstitial fluid colloid osmotic pressure.
That's the osmotic pressure from the few proteins that do manage to leak out. They are in the tissue space, so they pull a little bit of water, OUT, into the tissue.
Okay, so you have these 4 forces in a constant battle. What's the net result?
It depends where you are in the capillary. At the beginning, the arterial end, blood pressure is high. The push-out forces win. You get net filtration. Fluid sprays out into the tissue carrying oxygen and nutrients.
And at the venous end of the capillary?
By the time the blood gets to the venous end, the hydrostatic pressure has dropped significantly. Now, the suck-in force, the plasma colloid osmotic pressure, is stronger. So you get net reabsorption. Fluid comes back into the capillary, bringing CO2 and waste products.
But here is the critical catch, right? The math doesn't quite zero out.
It doesn't. And this is a fundamental design principle. The filtration force is slightly stronger overall than the reabsorption force. There is a slight constant net leak of fluid out into the tissues.
How much are we talking about?
Guyton says it's about 2 milliliters per minute for the entire body.
That sounds tiny.
It adds up. That's about 3 liters a day. If that fluid just stayed in your tissues, your blood volume would drop, your tissues would swell, and you would die from circulatory shock within about 24 hours.
Which brings us to the final unsung hero of our story. Section 6, the scavenger, the lymphatic system.
The system everyone ignores until it breaks. Its first job is to handle that 3-liter overflow every day. But it has a second, even more critical job, dealing with the proteins.
The proteins that leaked out.
Right. You always lose a little bit of protein into the tissue fluid. But here's the problem. Those proteins cannot get back into the blood capillaries at the venous end. The concentration gradient is wrong. They are stuck in the interstitium.
And if they stay there, they will act like little sponges, attracting more and more water and causing massive swelling.
Catastrophic swelling.
Correct.
The lymphatics are the only route home for those proteins. Guyton is very explicit about this. Failing this leads to death in 24 hours.
The structure of the lymphatic capillary itself is just genius. Guyton describes the cells like roof shingles.
It's a perfect description. The endothelial cells overlap, but their edges are loose and unattached. They form tiny flap valves. And these cells are tethered to the surrounding tissue by things called anchoring filaments.
So when the tissue swells with excess fluid,
that swelling pulls on those anchoring filaments. It literally pulls the shingles open, the windows open up, and fluid, proteins, bacteria, whatever's in the tissue rushes in.
And what happens when the pressure inside the lymph vessel rises from all that fluid?
The pressure on the inside pushes the flaps closed from behind. It traps the fluid inside. It's an automatic one-way pump that is powered by the very swelling it's designed to relieve.
I want to go back to that negative interstitial pressure concept for a second. Guyton is really insistent that the space between our cells is normally under a vacuum.
About -3 to -6 millimeters of mercury. This is a vital and often overlooked concept. Think about your skin. Why is it held tightly against your muscle? Why doesn't it just slide around like a loose suit?
I always just assumed it was connective tissue, holding everything together.
That helps. Absolutely. But Guyton argues that the primary force is the vacuum. The lymphatic system is constantly sucking fluid out of the interstitial space, creating this negative pressure that effectively vacuum packs your tissues together.
So if you lose that suction,
you get edema, the pressure becomes positive, the tissues get pushed apart by fluid, they separate. That's why you can press your thumb into a swollen ankle and leave a dent, what we call pitting edema. You've broken the vacuum seal and pushed the free fluid aside.
One last concept from Guyton on this, the tissue gel.
Ah, yes. This is another mind bender. We had this image of our cells floating in a little pool of water, but they aren't. The interstitial space is filled with a dense brush pile of proteoglycan filament. The water gets trapped in this mesh, forming a gel.
Like water in a sponge.
Exactly like water in a sponge. This is critically important because it prevents gravity from pulling all the free water in your body down to your feet when you stand up. The water is stuck in the gel matrix.
So when you see edema, that means the gel is completely saturated.
Exactly. You've overwhelmed the sponge's capacity, and now you have free fluid sloshing around, which is always a sign of pathology.
Okay. We've covered all the parts. The pump, the pipes, the exchange, the cleanup crew. Now let's put it all together. Section 7. Integration. How does the body regulate this whole show?
In the end, it all comes down to regulating cardiac output, how much blood the heart moves per minute. And there are two fundamental ways the heart adjusts its output: heterometric and homometric regulation.
Those are fancy words. Let's decode them. Heterometric is basically the Frank-Starling law.
It's a beautifully simple concept. Stretch equals snap. If you get up and run, your muscles start pumping more blood back to the heart. That increased venous return physically stretches the heart chambers.
It fills them more completely.
Right, and that stretch aligns the actin and myosin filaments inside the muscle cells to a more optimal length, allowing them to pull harder on the next beat.
So the heart automatically pumps out whatever it gets, more in, more out.
No nerves or hormones required. It's an intrinsic mechanical property of the muscle itself. It's an automatic matching system for input and output.
Then what is homometric regulation?
That's where the nervous system steps in. Homometric regulation is about changing contractility. The sympathetic nerves release norepinephrine, which acts on the heart cells to make them squeeze harder without being stretched more.
It's like a turbo boost for the engine.
It's a turbo boost. It shifts the entire Frank-Starling curve upwards. For any given amount of stretch, you get a more powerful contraction. And this is how we can explain the famous transplant paradox.
I love this one. It feels like a physiological riddle.
So you take a patient who has had a heart transplant. The nerves connecting the brain to the heart have all been cut. The brain cannot directly talk to the new heart. Yet if that patient gets on a treadmill and starts to exercise, their cardiac output goes up, just like anyone else's. How?
It shouldn't work. The brain can't tell it to beat faster or harder.
But it does work, for two reasons. First, the Frank-Starling mechanism is still perfectly intact. The muscle pump in the legs sends more blood back, the new heart stretches, and so it pumps harder. Physics takes over.
Okay, that's the heterometric part.
Right. And second, during exercise, your adrenal glands release adrenaline into the bloodstream. That adrenaline circulates throughout the body, floats to the new heart, and stimulates it chemically, increasing its contractility. That's the homometric part.
So even without the direct wiring, the pump still responds to the demands of the system.
Flow is not accidental. It obeys laws. The whole system is integrated.
Let's try and wrap this all up. We've journeyed from the explosive pressure of the isovolumetric contraction in the ventricle to the compliant smoothing of the aorta, the blinking lights of the precapillary sphincters, and the quiet, constant suction of the lymphatics.
It really reframes the whole body, doesn't it? It's not just a pump and pipes. It's a constant dynamic dialogue between force, form, and fluid.
And I want to leave our listeners with a final provocative thought that came up when we were preparing for this. It's about the imperfection of the system.
The capillary leak.
Exactly. We just spent all this time saying how amazing and elegant the body's design is, but the capillaries leak. They lose 3 liters of fluid a day. They lose precious protein. On the surface, it seems like a terrible design flaw.
But is it? Think about it. Because they leak, the body must have a lymphatic system to collect that fluid and drag it back to the circulation. And what is the crucial function of the lymph system on that journey home?
It runs the fluid through lymph nodes.
It runs the fluid through lymph nodes. It forces it through a screening process. It scans every drop for bacteria, for viruses, for cancer cells.
So the leak forces the interstitial fluid to be audited by the immune system.
Precisely. If the capillaries were perfect or medically sealed pipes that never leaked, our immune system would have no idea what was happening out in the tissues until an infection was completely out of control. The leak is what drives the surveillance system. The bug is actually a feature.
That is mind-blowing. The flow is designed to fail, just a little bit, in order to keep us safe.
It connects everything. Pressure, flow, fluid balance, immunity. It's all one deeply integrated system.
If you want to see the diagrams of those lymphatic flap valves or get a better look at the pressure volume loops we described, go crack open Ganong's chapter, The Heart as a Pump, and Guyton's chapter, The Microcirculation. It is really worth seeing the geometry of what we just described.
Absolutely. Seeing the diagram of the Starling forces really makes that tug-of-war feel real.
Thanks for listening to this deep dive. Keep the flow going.
And stay curious.